Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome my colleague aus Münster, RAIMAR WULKENHAAR, who will tell us about quantum fields on non-commutative geometries. Meine Damen und Herren, RAIMAR WULKENHAAR, the floor is yours, take it away.
Okay, so hello everyone. So first, many thanks, Piotr, for inviting me to this worldwide seminar. So maybe as information for the participants, we met last December in Toronto, and I gave a similar talk where I had not much time, and I put maybe too much into it. And Piotr suggested then that I do it more slowly in this occasion. So I'm happy to do this, or I try. I have put a little bit more than in Toronto, but not too much, and it should work. But also, I really would like to encourage you to ask questions, because I know this is further away from usual talks you hear in this series. All right, so, okay, the plan is to tell you something about quantum fields and geometries. So I start with quantum fields. Of course, this is a absolutely huge subject, and I can only give a very, very rough idea. So maybe it's good to start with axioms, system of axioms. There are many of them developed over the in the last century, essentially. So very important are the Weidmann axioms. They, in some sense, they generalize the axiomatic setting of von Neumann for quantum mechanics to quantum fields. And then soon later, there Kastner, who improved it in a very important direction. And today, this is the most important setting, I would say. Osterweiler-Schrader found the Euclidean approach, which for my talk is the most relevant one. And then there's also more the approach of Atiyah and Siegel to topological quantum fields, and this is something else. I will not come to it. So important for us is that Weidmann and Osterweiler-Schrader, they tell us that quantum fields are distributions. So distributions are nice objects in principle, linear functionals, and if you, they come with topology, so they are nice things in principle. The only difficulty, but that's a lot of difficulty here, is that we should not multiply distributions. At least it's not so easy.
So I have a question.
Yes.
So you mentioned the axioms by Atiyah and Segal. So you mean topological quantum field theory?
Yes.
And I have always troubles with understanding what is the relation between those axioms posed by Weidmann and Haag and Kastner and those of topological quantum field theory.
Exactly, yeah. I have the same trouble, and I think there is not so much relation. They're not equivalent, and yeah. But mathematicians like them, but one should not call them really quantum field theory.
Mm-hmm. Since I have an impression that somehow this theory of topological quantum field theory ended up with investigation of some properties of manifolds, some geometric facts, and not necessarily construction of operator value distributions.
Sure, I completely agree. Yes.
Okay.
There is some connection in conformal field theories where both viewpoints come nicely together. But otherwise, it is somewhat apart, I would say.
Okay, thank you.
Yeah, I agree. So, let's focus on Weidmann, Osterweiler-Schrader, and distributions. And so, as I said, we cannot, at least not naively, multiply them. And it turns out that the difficulties become larger if we increase the dimension of space and time. Okay, so here is say a relatively modern approach. That's stochastic quantization. It's a formulation of the Ostweiler-Schrader setting of the Euclidean approach, which has some advantages. So here there is a time, but this is not the time of our world of Viking time. It's some additional fictitious time which is added. And the motivation is that it's a sort of ergodic theorem or ergodic hypothesis that under certain situations there are so the temporal averages for large time intervals coincides with the spatial average. And spatial average is with respect of a measure, and that's a measure of the Ostweiler-Schrader setting, which we don't have. So that's our aim, to construct this measure, which gives us then moments of this measure, which we don't have, but would be the Schwinger function we're interested in. And as a substitute for this problem, Parisian Wu proposed to look at, via this ergodic principle, to temporal averages in some additional time. So there we have to add here some white noise to push us everywhere to test the whole space. And then for time to infinity, this additional time, expectation values in this stochastic setting should coincide with the Schwinger functions which we are interested in. The advantage of this setting is it's a very clean formulation where a lot of analysis can be done, and there have been tremendous progresses in the last 10 years, especially due to Martin Heira and Massimiliano Bugnelli. Okay, so there's one term here in red. If you ignore it, then this is the Langevin equation, and one has very fine control about the distribution. So phi in dimension 2 and above is a distribution. You can find it. And then one sees the problem is worse. Okay, so roughly in dimension 1 x dimension, you get the Hölder function as solution. The exponent is 1/2 minus epsilon, and for every dimension you lose 1/2. So in dimension 2, you get negative regularity minus epsilon, but it's almost a function, and therefore in 2 dimension many things work. Then recently, in last 10 years, a lot was achieved, or well, basically everything in dimension 3. Where one has to work. And for us, the problem is dimension 4. And that's what I want to discuss now. Okay, so, but yes, okay. If this term here, this red term is absent, then of course it makes sense. We can do everything also in dimension 4, no problem. But then we want to multiply it, say, do some form power series in lambda, or say convergent power series, and this is difficult. One has to do something, and this something is called regularization. So one has to replace our space RD by some hypercube lattice or torus of some length and spacing, and then construct RD back in some limiting procedure. Okay, there are many ways to do it. That's maybe not so much the point here. What I want to say is that there is now a deep theorem by Eisenman and Dumont-Coupin that this procedure, which is very well understood now in dimension 3, necessarily fails in dimension 4. So in another formulation is that the lambda factor 4 model in 4 dimension is trivial. It means whatever you do, you regularize your theory and then try to remove the regulator go to your original setting, then this coupling constant lambda, this parameter must be 0, and you end up in the original formulation where this red term is absent and you just have the ordinary Langevin equation. So it's impossible to have this interaction nonlinear term in 4 dimensions. So that's the landmark result of Eisenman-Diemel-Cotin. So I should say this was conjectured already in 1980s. Eisenman-Fröhlich at that time proved that this same triviality holds in dimension 4 plus epsilon. And everyone expected that it should be true also in dimension 4, but proof was not produced. And therefore, then some hope came that maybe it's still somehow possible, but in the end, there's this theorem now, and the case is settled to negative. Okay, there is a poor man's version which looks at the so-called beta function. I don't want to tell you what it is. This is positive in this model, and this is a bad indication that it will not work. So, okay, there are other arguments. For instance, okay, concerning Yang-Mills theory. So in Yang-Mills theory, this beta function is negative, and people believe that for this reason, Yang-Mills theory should exist as a concrete theory in 4 dimensions. But this is a very, very hard problem. It was selected as one of the Millennium Prize problems. Okay, to not existence only, also with the mass gap, which gives the mass to the matter as we know. So, okay, it's a very hard problem, and one of the difficulties is that so in so-called infrared region, so at large distances, this shows confinement, and things, it's really a non-perturbative regime, and things become very difficult. So, okay.
Can you explain in terms of physics what is meant by confinement? What does it mean physically?
So roughly, so physically, you have your constituents of matter. They are so-called quarks, and they are not free particles. So they need. If you try it, okay, 3 of them are in the proton or the neutron, and you cannot separate them. It means they form bound states. Well, bound states are difficult. It's at high energy you can have a scattering theory, which is similar to ordinary concrete theories, but the problem of bound states is not understood.
Okay, so it's bound states. Okay.
Yeah.
Sorry, I have a question. Would you agree that somehow the situation in this scalar case, in the scalar fields, is somehow more difficult since there is a theorem which states that this quantum field theory is trivial? So in some sense, my problem is how to view this theorem, since there is some sort of no-go theorem.
It is a no-go theorem.
Yeah, that's something cannot be constructed, but does it mean that the situation is hopeless, or maybe our methods are not appropriate to tackle this case, this scalar case?
No, I would say if we only take this model as it stands in Euclidean R4 or Minkowski space, this is a no-go theorem. There is no way to construct this model. It doesn't exist. So the hope is that this, if you couple this scalar set interaction to a good model like Yang-Mills, so here I think of the Higgs field, then together there might be a chance. So there should be a scalar field in nature named the Higgs field. Well, it's a little bit different because then, as you know, the mass square has to be negative in order to support this spontaneous symmetry breaking. But yeah, the hope is alone this 5 to the 4 model will not exist for Milton, but together with all the good Yang-Mills theory, it should work.
Uh-huh.
This will be the way out.
Okay, thank you.
But okay, then, okay, well, as you mentioned, there is this difficulty that easy examples, relatively easy, like lambda 5 to the 4, will be trivial. Same happens to if you take quantum electrodynamics alone in 4 dimension, so not as part of a standard model. This will not work. And if you try to do something more realistic, like Yang-Mills or the full standard model, then this is infinitely hard. So, okay, and it's a relatively uncomfortable situation. And this brings me then more or less to what I want to tell you, is that, well, okay, if we can't do concrete theory in 4 dimensions in the usual situation, okay, let's try to see what can be done if we do quantum field theory on non-commutative spaces. Okay, this was at least a question a long time ago. For me, the motivation came from this influential paper by Cohn Douglas Schwartz on defining M theory on a non-commutative torus. So M theory is an extension of string theory, and okay. And so there, the important non-commutative space, the non-commutative torus, appeared. And well, this suggests the question that it makes, or okay, one should try to make sense of quantum fields on the complete spaces. Soon later, Schomerus, Sabak-Witten extended this idea to pure string theory, or at least with Liebrenz and so on. And okay, this is now 25 years ago, and well, my plan is to tell you something what happened in between, and okay, where we are. So okay, I have to say that I focus here on this Euclidean or stochastic approach via measures on space of distribution, not so this far away from the Weidmann approach. So it means we do not have any understanding of time in this setting. Traditionally, the time appears via Osterwalder-Schrader positivity, reflection positivity, which allows then this weak rotation of the physicist make very precise its transition between Laplace transform and Fourier transform. But we do not have this here. So it's in this sense, it's somehow formal. We do not have these axioms. We do not have Osterwalder-Schrader positivity. It's too early. But I should also say, also for Yang-Mills theory, we do not have reasonable axioms. So, okay, it's something for the future. So what we do at the moment is we want to learn how to build nonlinear things out of these quantum fields. So, because if you just take the linear theory, so distributions, then everything is as on manifold, everything is governed or should be governed. There are still things to prove by the spectral dimension of your Laplace type operator. Otherwise, it's the linear theory is the same. And what we want to understand is how to build nonlinear objects out of these distributions. And the answer is things are much better than the manifolds. And you will see throughout this talk, we can do something with the quartic model, so lambda 4 in 4 dimensions on 4-dimensional non-commutative space. Something which is impossible in the real world. All right. Good. Okay, so let's start. We start first with the linear theory. And but we prepare already a little bit for nonlinear interactions. Okay, our setting is Fréchet's star algebra, where for the moment we ignore the algebra part. This comes later. So, and we assume that as a vector space, it's a nuclear vector space. And we restrict first our attention to this real subspace of self-adjoint elements, as A sub star. So, in this setting, we have the Bochner-Mindus theorem. So, Bochner is for finite dimensional spaces, and Mindus then the extension to nuclear spaces. Okay, so given a functional on this A star, which is normalized, continuous, and of positive type in such a sense. Okay, let's go back. Okay, there's a certain positivity condition, which looks strange, but there's a reason behind. So, given these conditions, then the theorem tells us that there is a unique Borel measure on the dual space, so essentially on the distributions, such that our given functional is the Fourier transform of this Borel measure. So now you can.
Wait, Raimar, is F your script F a functional?
Yes. Yes.
Is it is linear, right?
No, it's not linear. But was it linear? No, it's not. No, it's not. It's not linear. Definitely not.
No, that's exactly why it's not a functional. Okay. Mhm.
It's functional.
The
Yes.
functional.
Yeah.
I
So
have a problem since this right-hand side of this formula wouldn't give you a real number, yes? This functional should go into real numbers, but you are taking e to the power I.
well, okay, so let's check. It's okay. Assume everything is settled. We have this condition, and now you do the following. You take you place A by AI minus AJ. You have it here, and now because phi is linear, so yeah, phi of AI minus phi of AJ is phi of AI minus phi of AJ. So, and then you multiply with CI, CJ complex conjugate, and then you assemble everything here to a manifestly positive quantity.
Oh, okay. So it is not obvious. Okay.
Well, no, it's almost obvious. If so, phi is linear, and then you reduce manifestly to the norm square, modulus square of complex number. It's directly. So if your function is of this type, then this positivity is automatic. So therefore, this condition is necessary, and the theorem is it's also sufficient, and this is deep.
Sorry, I know it's completely
Still I have a
trivial. Yeah, go ahead.
Sorry, go on.
Now, I'm pondering about the question about the reality of F, because there's an I in the exponent. So how does it go away? Can you say it again, please?
It's not, no, it's, I see. Right. This is typo. Thanks, Piotr, this must be complex.
Okay.
Yes.
You are not claiming that this value
No,
be
it's
real, but it is still positive.
Yes.
Type. Okay.
Thanks a lot.
Okay, thank you.
I can send you the slides and then I correct it. Thanks a lot.
Yeah, of course. Yeah, thank you so much. Yes.
Yes. Okay, so then there's a very important class of examples, namely the Gaussians. So if you take any inner product, which in this setting is called covariance, you take x of the negative inner product, it's a Gaussian, then by there's a sure product theorem a long time ago, which guarantees then that this functional is positive, of positive type in this sense. And therefore it defines a unique measure, and here it's called d mu c. So this is the free field which always exists for free for any such covariance. Okay, this we always have. And the challenge is then something else. Good. And now let's do a first step towards algebra, and let's assume we have in our Frege algebra matrix units in the sense where the multiplication is continuous. All right, and somehow we take this sort of basis and then assume this is a strange assumption that the inner product for these matrix units has this particular form. So, the motivation for this particular choice comes later from the Kontsevich model, where exactly this is realized. There are many, many more possible choices, but we take this particular one. So, and throughout this talk, I take only this particular inner product and the corresponding measure, and I work with it. Good. So, this gives me a measure which would be a free scalar field on my Frege algebra, essentially. So I should say these EK, they will play the role of eigenvalues of a Laplacian. So, and as you know, the growth rate by Hermann-Weyer's theorem determines then the spectral dimension, and this will be very important for studying details. Good. So now comes the product, and here is definition of the spectral dimension. That's the usual one. That I have here 1/2 is related to the fact that normally you consider you make the spectral dimension with the Dirac operator, and then you don't have this 1/2. So the square root goes to a certain Dirac operator, and then this is the usual definition of the spectral dimension. Good. So and it should be true, but there's still some work to do, which I'm trying to understand. The similar is in this approach of stochastic analysis. That so the space of distribution is huge, and in fact, the support of this measure should be much smaller and much nicer subspace. So in the usual theory, these are the best of spaces. And so one has to come with an analog of these best of spaces in the spectral setting. And that's something I want to do in the near future. And this will be important that because it then determines which products of distribution have a chance and how much one has to work. But this will be in future. Well, for the moment, we do something else. We formally define the trace of phi to the n, phi such a distribution in this way. But of course, this infinite sum has no chance to make any sense, simply because here this tensor product is by no means Frege. So therefore, applying the n-fold tensor product of phi to it has no chance to exist. So, and then we follow the usual procedure of complete theory to make sense of it. We restrict here this infinite sum to finite one. So capital lambda is then a certain parameter. So, the script n appeared before. The script n I had here as a parameter, and this will become important later. So lambda is the cutoff parameter, and my prefactors here of the trace, they will then depend on lambda, and one has to arrange things so that limits exist. Part of it is to find out which moments of this measure are dangerous. I'm a bit vague here. So dangerous. So in the real world, for instance, if you have electrons, then dangerous are, for instance, the mass and the charge of the electron. And something analogous will be declared as dangerous, and then there are more harmless ones, and they should have a limit.
Sorry, I have a trivial question about your regularity conjecture. So I'm a little bit behind. When you define this infimum in your formula, what are these numbers, EK?
So EK, I had, they defined my scalar product here. They are here. They are
Okay.
given. And so this inner product is essentially the inverse, it's the usual inner product in Fourier space with the Laplacian. So maybe I go back. So okay, here it models this situation, and then you solve essentially the heat equation with this Laplacian. Laplacian is replaced by some non-commutative Laplacian, and EK are the spectral values.
Okay.
So that's the idea, and this should determine then the well, first the spectral dimension, but also the say degree of irregularity of my distributions.
And it was on your previous slide that they are growing, right? That EK are growing when K goes to infinity.
Well, it's just the order.
Increasing sequence of course.
Yeah.
Okay. So the spectral radius is getting bigger and bigger. Okay.
Yes.
Thank you.
Okay. Good.
If I may, short question. What
Sure.
is the role of the parameter n in this formula?
Very good. This will come. It will come in two versions. So it will be the appropriate cutoff will be the size of the matrices. Then I denote it by straight n. This is the traditional situation. In this field theory model, this script n will be related to the scale of non-commutativity. One can see it essentially here. It must be some dimension for quantity related to the Laplacian, and I want to vary something, and this will, in some slides, be say this theta parameter, the scale of non-commutativity.
Okay, thanks.
Oh, sorry. No. Yeah, okay. So I'm here. Good. All right. Okay. No. So now this n becomes important. All right. So this part d mu e was my Wörner-Minus measure, was defined by this inner product and the sequence E. So now I want to add some regularized potential in the usual way. And the Z is such that this is a measure. So the integral over the whole space is 1. So one way to view it is, okay, let's suppose this is polynomial. Let's go back. Then I can expand the exponential, and then I have some products of traces of phi's integrated against this Gaussian. And Gaussian have the property that only, yes, so this fixed theorem contribute. This can be seen here. Okay. Right. So if you have this, you want to have moments of this measure, then the idea is you write A as T1 times A1 plus T2 A2 and so on. Use the linearity, differentiate with respect to T1, T2 and so on. This brings down the phi's, and then you evaluate everything at T equals 0. Then you get the moments you want. But you do the same here, and then you see that the result will be a product of these covariances. And takes two elements here, AI, AJ, then as arguments. And this is a mixed theorem that whenever you have integrate product or moments of Gaussian, this factorizes in product of pairs. So graphically, a pair we represent as an edge in a graph, and it's important that every edge in this setting comes with factor 1 over n, and there are certain data, so Kronecker deltas. And the weight of an edge will be 1 over ek plus el, and they will become relevant later. So now, no, here. Okay. For every edge, we have factor 1 over n and Kronecker deltas. So then, so when people term trace phi to the p will be a p-valent vertex, and with this prefactor n here, we have again factor n. And then we get several Kronecker deltas, and in the end, from these traces, essentially we sum over them. And okay, because Kronecker delta summations will be easy and immediate, and some will remain. And the convention is that out of every remaining summation, we also take out a factor n. And
can you give some physical meaning to this factor n?
Well, physically, well, it will be this noncommutativity parameter, but it has, as we see in a second, a very important topological meaning, because it, so these closed loops, the summations, they are phases. Vertices come with factor n and edges with factor 1 over n, and then if we count the total number in n, you have n to the power number of vertices plus number of phases minus number of edges, and this is the Euler characteristic. So it's more a combinatorial meaning point.
Okay.
So this I would like to say here that there is a natural expansion of any moment by the Euler characteristic and to the Euler characteristic. And then so we have a natural substructure that the moments they become formal sums in the genus of contributions, so homogeneous contributions of a certain genus and a given number of mark points. So this is now important that for simply combinatorial reasons, we get our moments expanded into topological contributions of the same topology type. So it's important this this series here is a formal series. It will not converge. The reason is simply if here you have something positive, say p is even, and if it converges, then it would also converge for negative n, and this cannot be. So it's the usual situation as in quantum theory. This can only be a formal series, but nevertheless, it's a very convenient point of view. All right. So okay, now the strategy. This slide is maybe not so easy to understand. It tells you the strategy, and there will be examples where we then follow the strategy. So okay, the strategy is that we use identities which result from integration by parts, and these identities are called Dyson-Schwinger equations. So and then they also come with the grading by the Euler characteristic. So they are complicated identities, and if we grade everything by the Euler characteristics, then we take advantage of relations. Okay, moments, humans, okay, they are graphically, as I said, represented by genus G Riemann surface with some boundary, and on the boundary we have we have here these p-valent vertices, and then they come from the expansion of this measure you see here. In addition, we have these objects which represent one-bland vertices. So, and the convention is they sit on the boundary of the Riemann surface. Good. And then we have all these labels EK. Somehow they label sections, sections of the boundaries. And there's something which will be clear, will come later. We can extend certain of these are real numbers. We can make them complex and take them anywhere or in projective space. And this will be an important step, and here it's a little bit mysterious, but it will become clear in examples. Good. So, okay. And then what one finds in these situations is that if you restrict these differential equations to the highest Euler characteristic, then only something of the highest Euler characteristic can contribute, and you get some complicated linear equations for the amplitude, which has the highest Euler characteristic. So this will be disk amplitude, has the highest Euler characteristic, and with the least number of one-way vertices, and this gives a function which later will be called y. And then there are two things we can do. We can insert more one-way vertices, and turns out this is relatively algebraic or a combinatorial problem, and there are indications that this links to questions in free probability. And this part is more or less easy. There is a more difficult part, namely a topological version in decreasing Euler characteristic. And this is, well, it's a huge topic nowadays, pioneered by Hénard and Orentin long ago. And this connects to many other areas in mathematics, and I try to give some feeling about it. So it's a topological version in decreasing Euler characteristic, and it starts from initial data. One of them is the disk amplitude, and then we need something else, which is called x. So this will come. Okay, this is overview, what will come, and now we study this procedure in two examples, and one is the cube model or the Kontsevich model, and then the quartic model later. Okay, so now this potential P, which we had here, okay, this P we take now a cubic potential. All right, the main term is here the one in red. Everything else is necessary for optimization, and I say more about this later. So in the first step, we ignore all these pieces, that's what I say here, and only take lambda third pi cube. And also our algebra will be just n by n matrices, and this parameter script n will be just the size of the matrices. And all these other terms are absent. Good. Okay, the discovery of Kontsevich was that this particular choice of a matrix model with exactly the same, well, Gaussian measure, which we had, produces the generating series for intersection numbers on the moduli space of stable complex curves. And on one hand, okay, this is the relation. On the other hand, this cubic potential, the corresponding, say, equation of motion, is the matrix version of the Airy function or the Airy equation. And it is known or was known already that this particular function relates to the KdV integrable hierarchy. And this settled a conjecture of Witten. But the main step was to identify that this generating series relates to this cubic potential, which was a remarkable step at this time. Okay. And now we study something which was proposed here by Hénard and Orentin. It's a very nice idea. So Kontsevich only looked at the partition function itself. With optimization, only this d mu without the z viewed as a function of E. But we can do something else. Take the honest
N are Hermitian, yes, matrices.
that you asked. Yes. The phi are Hermitian matrices. Yes.
Okay, so we are integrating over Hermitian matrices. Okay.
Yes, this Hn is the Hermitian matrices, Hermitian n by n matrices. Yes.
Okay, thank you.
Okay, and well, phi of I used the notation before. So for finite dimensional spaces, of course, the dual space is the same, and phi of E, say A1, A1 would be phi A1, A1. So it's a little bit redundant. So, okay, the convention, okay, well, this suggestion is look at these particular moments where you will integrate with this cube measure diagonal matrix elements. And up to some shift, which, okay, for reasons maybe not so important, defines certain, well, certain numbers and call them W A1 up to AN. So, and each A1 and so on, they run from 1 to N. So again, it's a formal series in 1 over N squared. To make sense of them properly, we assume these AI are pairwise different, so N is large enough, and this C stands for cumulant. Okay, these are basic objects. A remark, this links to what I said here, this algebraic recursion. Here I consider different moments, so roughly everything can be understood as permutations. So here I have a permutation of n elements, and each permutation, so I have n cycles of length 1, and here I have 1 cycles of length n. And this 1 cycle of length n can be reduced, to a single cycle of length 1, named here this object. And then there are just combinatorial formulae, and the formula is given here. It's not important for us. Just want to mark this choice that we look at the diagonal ones is by no means a restriction. One can do it much more generally. But if you understand these W's, then you understand everything. So this part is easy. The hard part is to understand these particular W's. So now there is this integration by parts. And then what we, okay, after some work, one gets at such an, arrives at such an equation. So don't ask me, it's work. The strategy is integration by parts, but one has to know what has to be done. Okay, so please accept this equation. And now let's look at special cases. And the first interesting case is that here.
Just explain the meaning of this symbol, this union with plus. This is disjoint union, or? Exactly.
So, okay, you have a set of n elements, and you sum over all possible splittings of this set into 2, such that the union is everything and they are disjoint. Exactly.
Okay, thank you.
Yes. Okay, the simplest case is that so this set is empty, then okay, then you get here the square of W0A, nothing else. Then this is EA square. This term is absent because genus -1 doesn't exist. This term is there, okay, this exists, and here, because n is 0, this is also not there. Okay, so we get this term squared, EA square, and such a different square. Okay, this is an equation which can be solved by Riemann-Hilbert techniques done by Makienko and Semenov. And here's the solution. By understanding branch cuts arising from this difference quotient, they found this solution.
Can you please say again what is disjoint in this notation?
Well,
Disjoint.
It's subsets, and they as subsets they are disjoint.
Subset of a set of elements from A1 to N.
Yes.
Okay, thanks.
So you have additional indices A1 up to N, and you distribute them in all possible ways on the 2 parts. Okay, so and now at the end, someone want to go to the limit n to infinity, and then you see that there can be troubles. Depending on how fast these e's go, this sum in general will diverge. And also here, there is some consistent condition that is even more dangerous. And depending on the spectral dimension, encoded in growth rate of the EAs, one has to do something, and this leads then to the necessity to add all these other counterterms. This modifies a little bit the equations, and then everything works again. And one gets here then to normalize sums where then in limit everything converges. So this is the motivation, and everything can be done in dimension between, say, 2, 4, and 6. For some technical reasons, only even part is relevant. Okay, so this solves the problem, the initial problem, the disk amplitude. And then, if one looks carefully, so one gives oneself G and N, then in this highest Euler characteristic, one sees that it's linear or affine in the highest Euler characteristic and nonlinear only in something which is when Euler is negative. So in the lowest, so means by modulus largest Euler characteristic, it's affine, and nonlinear in the higher Euler characteristics, which by induction we already know. So in principle, we get just affine equations. And with work, one can solve them, but it's better to think and discover the structure, and then use a universal method to solve these equations. And this universal method is topological recursion. So, okay, now I tell you how to reformulate everything. And to arrive at the starting point of this universal method. And the first step is to observe that, okay, for this EA, you can replace them by any complex number. Okay, this EK we should keep, but EA can be anything, and also here this EAJ, they can be anything. So the equation makes sense without modification, and that's what we do. So, and we want to get rid of these square roots, and so it's better to replace these square roots by new variables. Okay, this one we call Z, and this we call ZL, or no, epsilon L in this case. And we just reformulate our equation in this way. We should keep here these summations because in summation it's very important that we have our original variables. But all others are free. And the relation is that if now these are now functions of many complex variables, if we evaluate them, the z's equal to epsilons, then we get our previous moments essentially. Okay, and then having this complex equation, and in particular W0. Well, 0, 1 of Z can be found, so this is minus Z plus the sum 1 over epsilon L, and then in the parentheses Z plus epsilon L. Now in this one can check that the next solutions are these. Okay, it's relatively straightforward, but still not where we want to go. It turns out that next one can inductively show that, okay, here you see something very typical. Okay, W02 is special, but then later also continue this business, you see that you get odd functions in Z. And this is true then in general. If in one particular variable, it's always odd. This you can prove from the previous formula. And if you use this, you can rewrite the previous formula in such a way where you distribute. So previously you had Z and Z, but you can artificially make a minus Z in collect terms. So here in particular, this W02 has here a minus, and previously we had a plus. But this minus comes from absorbing here one particular term. So there's some rearrangements. And you get such an equation after some work. Also, this W01 is not the same. There's a minus sign. So previously, here, we had here minus set and there plus. So there are some changes, but after, okay, one can arrive at such an equation. Okay, and now we are in business. So these two equations are the starting point or the input for a general procedure, and this is called topological recursion. So, and it was discovered by Inhalt Orenthal that many matrix models can be put into such formulations where you have such, okay, everything is governed by functions W of several complex variables. And there is something which is a linear object. The minus is here special, must be generalized, and a quadratic one. So, okay. And yeah, okay. And the input data are two ramified covering X and Y of Riemann surfaces. So in previous case, it was just complex projective space. And they should satisfy some polynomial equations, and this defines, this gives the name of a curve. And then there is also a universal object called the Bergman kernel. It's a normalized symmetric bidifferential on the sphere of the Riemann surface. And okay, then there's a formula to proceed. I want to just say here that this universal structure was discovered for matrix models initially, and then was later found, well, soon later, that the same structure is present in many areas of mathematics. So, for instance, in Mizrahi's recursion of Will-Peterson volumes of moduli spaces of border hyperbolic surfaces. Then there is this ELSB, so Ekedal-Landau-Shapiro-Weinstein formula, which expresses certain Horowitz numbers. Well, there are many variants of Horowitz numbers, but let's say simple ones. Is in sorry. That integral over greatest classes, psi lambda classes on the moduli space of curves. And much more general, there is a notion of cohomological field theories. It's generalizations of these characteristic classes, which also fits perfectly into the setting. So this is a general remark, and now I go to the formulae. So assume we have this spectral curve, this data with some assumptions. Okay, let's ignore them here. And then this Y is our W01, and this Bergman kernel gives this W02, which is relatively universal. And the X is especially responsible. So X is a ramified covering line, means in general it is D plus 1 to 1. And the fiber generically consists then of D plus 1 points. There's a principal image, which set, and then the other images. So, okay, and now let's suppose we have this family of WGONs, and they satisfy two conditions. So one is the linear condition. If we sum in one variable over the fiber, then because it's a symmetric function, this is a function then which projects downstairs of x of z. And if we do the same in this quadratic relations, rec means here on the diagonal, this W02 has a pole diagonal and has to be somehow removed. But otherwise, you can go to the diagonal. Okay, so, okay, now these are then, because they are symmetric in the pre-images, they project to functions of x of z. And x of z is no special point. Okay, so I said generically we have D plus 1 pre-images, and the ramification points are those where two of them, or maybe more, come together. But downstairs projected, there's nothing special. And therefore, it's absolutely natural assumption, which is basically always realized in these matrix models or more, that L and Q are holomorphic at the branch points. And then there is a universal, well, after some another condition, formula which evaluates all these WGNs in terms of those which we already know, which means G prime or 2G prime plus N prime is less than, means they have a larger Euler characteristic than the ones which we are interested in. So it means recursively, starting from W01, 02, we can compute everything as soon as we know that, well, we have this holomorphicity property. I don't give this formula. Well, I think it's still complicated, but it's a very nice structure, at least under some technical assumption, which in most cases is satisfied. There's a certain projective property. It's okay. So everything boils down to taking residues of some universal kernel, which is built out of y and omega 02, and then one is multiplies here this. Also, sorry, this right hand side where you move the trivial contributions, 0,1 contribution, and get something that so the next omega, so WGN, which you want to know. Okay, so in case of constraint model, this X is very simple, Z square, and now this here the pre-images are just Z and minus Z. So X of Z is X of minus Z, and then the sum here means so Z hat 0 is just Z, Z hat 1 is minus Z, and this is just the relation which we have here. And also the other one, and it's okay, it says that the sum must be holomorphic, in fact 0, and also here means so the unification point is 0, where the two Z equal to minus Z come together. And here the requirement is that the right-hand side is holomorphic at 0, which is obviously the case for generic Zi, also different from branch points. So then, so this we have checked it, and then there's a universal formula so that we get all step by step all WG with any index. Okay, and therefore now the conservation model is solved. Good. The remark interesting for the main top for algebraic geometry is that if we now expand these WGNs near an entropy of communication points, so for conservation model, it's only at 0. So coefficients at 0 have a meaning, and that's more general true. We can expand any any model captured by topological recursion near an n-tuple of ramification points, and then the expansion coefficients can be universally expressed in terms of intersection numbers of characteristic classes on moduli space. Another remark is that if we do not have this projection property, this one, we still can do a lot, and this leads us to an extension called block topological recursion, to which I will come. Fourth remark is that out of these WGNs, one can, by deformation techniques, produce tau functions of KP hierarchy. Probably means formula in 1 over n. And so that there is always a relation, so every topological recursion, at least, well, not the block situation, but otherwise any other relates to integrable hierarchies, which is also very remarkable. So in case of this example, the constraint model, this is specialized, well, it's specializes to KDV. In general, it is KP. Okay, then a remark which is interesting from geometry. It was recently discovered that there's a very nice, okay, well, motivated by Horowitz numbers, identities for Horowitz numbers, that one can define a universal relation between two families of functions, W and W. Check. And it's completely natural. It's something with Horowitz numbers. And in relation between W01 and the check version happens to be exactly the art transform of Voiculescu between free members and free cumulants. So in this, well, this was known in the beginning, and then surprisingly it's continuous. So the relation between W02 in terms of the check versions of not large or not higher Euler characteristic also appeared before, namely as the relation between characterized as second order freeness, which was proposed long ago by Collins, Mingo, Schneider, and Speicher. So okay, and this means there's something going on, and the proposal is that well, this relation which they found defines what is defines freeness of higher order. Also, not only the planar case, but something more general. And there are exciting developments currently going on.
Sorry, where is he from, Mingo? Is he from Western University?
In Kingston.
Yes.
Yes. Yes.
And as I pointed to, you have an I missing in Schneider.
Ah, yes.
So it's 2-0 for us. We found no mistakes.
Yes, thanks. Okay. Yes, and okay. Then, in general, this relation is if you change x and y, and was conjectured and meanwhile. Okay, so yeah, okay. Now, what's the relation to our topic? This was already done long ago by Ralf Grosse and Harald Steinacker. They found that this classical action on a non-commutative space, namely on Monal space, can be mapped to the conservation model. And these additional terms, which I had them here. These additional ones, they are necessary for renormalizing this model. So, conservation model, everything was finite or large matrices, but Monal space needs essentially infinite matrices. You have infinite matrices of coordinate operators satisfying such coordinate commutation relation of the Monal algebra. And they found a way to map this complete theory model, this is quasi action, to the conservation model. So therefore, the relations of conservation model can be immediately translated after renormalization to this particular complete theory model. And now I can answer this question on n. The script n is exactly theta over 4, where theta is certain parameters in this big theta matrix. So okay, and so as said, we have so the previous straight n is now replaced by script n, and we are interested in the large n limit, and now this is a large theta limit, so it's a limit of infinite non-commutativity, which is the interesting situation. Whereas the limit of Monal back to ordinary commutative space would be theta to 0. So it's the opposite limit, which can be treated here. So interestingly, so here the first terms in whatever. The first terms they make up this if there's 1, they produce these eigenvalues E, which I had, and give rise to this particular Gaussian measure. As you see here, this explicit experience of X destroys translation variance, but in the limit that theta goes to infinity, because here it's the inverse appearing, we restore translation variance. And we get honest Schwinger functions on normal RD, at least a map to it. And interestingly, at least the two-point function has this famous Osterwalder-Schrader positivity in dimension 4 and 6, not in 2. I have no good reason for it. But okay, in 4 and 6 dimension, it is positive. It was a good indication, but unfortunately, the whole theory fails because of this characteristic dependence of the two-point function. Z1 plus Z2, this behavior destroys positivity.
Sorry, I have a quick question.
Yeah.
Should we somehow expect that in this infinite non-commutativity limit, one gets something which is free, like in free probability?
So freeness, as you know, there in the Gaussian model, then you suppress the non-crossing partitions, and you get it's not completely free. You get something which is simpler and planar, and this happens. So there are only contributions from the planar sector, not only the free, but also the W. Zero ends, so they contribute.
Okay, thank you.
It's almost free, but not entirely. So it's still interesting, but not interesting enough because we do not have positivity. Yeah, and so for me, this was the motivation that maybe we should keep the higher genus contributions and try, in some sense, so keep theta finite sum. As I said, this sum, the series in the genus will not converge, but there has been enormous progress recently, so in this paper, where they were able to say something about this estimation connected to techniques which are also very fashionable. They're called researches. So, okay, means that there is some hope to say something about finite theta, and also to come, hopefully, maybe to theta to 0 limit. But then, of course, we can expect to have something translation variance. So the axioms will then fail at this point. Okay, so in the meantime, I would like to tell you something about this quartic model. So, I have this potential, and now P is 5 to the 4, the quartic potential. And then I repeat the steps which we had previously. So now interesting is now the second moment. There is no first moment because this increases to 0. The second moment is the first to study. And then, as I said previously, we get Gaussian equations. They can be complexified. And here is the complexified equations for the leading contribution, the disk amplitude. So the two-point functions and the leading part in 1 over n. So it's a closed equation for this planar two-point function, which we found long ago. And but okay, so we had to stop because we had no idea how to solve it. Okay, it can be formulated as an integral equation for trivial reasons. Okay, the sum you write this integral over a discrete field measure. But this has advantages. So then now let's start from this equation and suppose O has good properties, so it's no longer a sum of Dirac, but Hölder continuous, and then there are some techniques available. Okay, this we knew early, but still, because of this nonlinearity, we were not able to do anything. But in the meantime, we have the solution, and so I describe it for you. Starting point is such an ansatz, which we had already long ago. This would be the natural ansatz, which comes from theory of singular linear integral equations. So if there's not this term, only here the singular, you take it apart, this singular term, then the natural answer is always this one in terms of the Hilbert transform. You see here this characteristic kernel, which appears in the equation before. But here, this answer does not solve our problem. That's the difference. But we can do something else. So we suppose this angle function, which is part of this theory, is the imaginary part of some complex logarithm. It involves some function RD, which must have a branch cut, and the natural function of the branch cut is such as D is transform. Okay, and now the measure in C this transform is some rho lambda, which in the beginning has nothing to do with the previous rho naught. So let's go back. So here we have some rho naught, which is given. And now this rho lambda here is something else. And now the miracle is, if we choose this rho lambda such that this rho lambda is rho naught of RD, which implicitly depends also on rho lambda, so it's a complicated implicit relation, then the non-integral equations which we had previously, so this one is identically satisfied. So this, okay, took us a long time to arrive at this, but it's a simple observation. And it's elementary to prove using very old mathematics. So the case that rho naught is 1, this is two-dimensional Moyal space, then there is nothing to do here because then rho lambda is 1, and we get it explicitly. We get here logarithms. The inverse function is the Lambert function, and then this gives the idea to how one arrives at it. And this was the big step to see that the generalization of the Lambert function leads to such a formulation. Okay, so now we have solved the equation, and there's something important. So one very important case is four-dimensional Moyal space, so really four dimension, and there the spectral measure, at least in the limit, back. Okay, so I take here this case of Moyal in four dimension, and then in the limit, this sum, at least in some weak sense of convergence of measures, converges to the situation that rho naught of T is T. Okay, and then well, the problem boils down to this one. Rho naught is of T is T, so it's the identity. So we have rho lambda is of R4 is R4, and R4 was this function we have rho lambda. So it's just then a Fredholm integral equation, and okay. But now first discuss it. So the expectation was, of course, that rho lambda behaves similar. So if rho naught of T is T, then rho lambda of T should also be T up to logarithm contributions. And then you see that this integral here, well, okay. In order to make this integral converges, you need some power epsilon of this T plus X downstairs, and then roughly you can, of this X square, you can only compensate an epsilon or 1 less epsilon, and you get something which here in the second term grows as X to the power 1 plus epsilon. And then with the signs are such that this term wins, and this R4 okay, reaches maximum and then goes down, and therefore the inverse which we need is not defined, and this is again our triviality problem. So this is what we thought would happen, that we get precisely because of this discussion our triviality problem back. But things happen to be different. It turns out one can solve this integral equation, for instance, by derivation theory, and gets hyperlogarithms and Riemann zeta values. And this can be summed to a remarkably simple function, namely the Gauss hypergeometric function. And dependence on the parameter lambda is in a very explicit, complicated form, namely inside the arc sign. So expanding the arc sign, of course, then gives powers of to even powers of pi, and they are precisely the Riemann zeta values. Strangely, that this works. And if you now expand in lambda, expanding here in x is easy, but in lambda, this produces all these complicated number theoretic expressions of complete theory, namely hyperlogarithms. Okay, so now we have something explicit, can solve it, and the important remark is that well, this effectively defines the measure, and we know the asymptotics of the Gauss hypergeometric function, and it corresponds effectively to a measure of reduced spectral dimension, namely 4 minus 2 epsilon pi over pi. So this means that because of this interaction term, we now effectively come into the good subcritical regime where we avoid triviality. So at least in the planar sector, the theory will exist or does exist. Well, it's clear. And the hope is then that this observation and well, the exact solution of the planar sector permits to solve this lambda field form model in 4-dimension rigorously. So, okay, this is a two-point function, but I want to remark that we understand the entire planar sector. There's just a combinatorial problem related to objects which appear also in free probability. Namely, there is an explicit formula which expresses higher endpoint function in terms of expressions which are in rational function, in numerators, products of two-point functions, and then very characteristic denominators. There are a certain combinatorial number of terms of them, and they are in bijection to Mrs. Catalan tables. So essentially, it's a Catalan structure of something which is also Catalan. And graphically, there are two parts. One here in the numerators, these are the green objects. They are non-crossing chord diagrams. They're Catalan and many of them. If they're n chords, they're Catalan and many chords diagrams. And then they form such a pocket. And inside the pocket, we have a pair of trees. And the trees are in a very precise sense dual to each other. And these are planar rooted trees, and they are also counted by Catalan n. If n is the number of edges then of these trees. So there's an iterated Catalan structure, and the number of them is this. So therefore, we understand completely the planar sector, and so interestingly, this is open question which I want to work on. Can this be understood as problem in free probability? Where we somehow the building blocks are these two-point functions. They are somehow the only non-zero free cumulants, and they build up then in this way the moments. Okay, just remark. And the rest I can go quickly through. We have the planar sector, and maybe this I should say, if we would do the same as in usual theory, take the linear theory and perturb, then this will fail in the same way as before. This is not what one should do. One should identify the planar part and solve it exactly, which we can do because of this relation to matrix models in geometry. And then we have a chance to go through. We get something, non-trivial. So, but we have to know we are not ready. We have to insert everything else. And as I said, these are formal series, and it remains to do something. So, and one idea would be to show that these corrections, they are not only formal, but they are asymptotic. It would be something, and there are ideas to do it, but we are not yet there. And the other possibility is to control to all genera and then resum, also possible. But that's something for the future. What I want to show you, at least some flavor, is that for finite n, we are not yet there to go to the large n limit. For finite n, we understand something about the homogeneous contributions. So here we right. So okay. So I said previously we had this linear equation, and we get then the immediate step this solution for this function r, and then we have an integral formula for the two-point function. In case of finite matrices, we can do more. We get an explicit formula, and this formula is shown here. So okay, there is this function x, okay, which comes out of the equation, and so roughly follow. Take this function x, and the condition is that okay, these little ek, they are saying okay, no, they're here. The previous capital E, so previously we had capital E1 up to En, and now we reorder them into little e's, and we take multiplicities. So, and condition is we have two parameters epsilon and rho, and x of epsilon is these given e's, and the derivative relates to the multiplicities. Okay, now x is x. And take y, very special, namely y of z is minus x of minus z. So this is part of something we had here. So essentially, part of this reappears now in this formula. And then define such a function P01 using products over the pre-images, and the marker answer is this solves identically our nonlinear equation. So the equation here is identically solved by this. Of course, we had insight from what I said previously. Good. So now we have to define our omega G. And they are, well, derivative of the logarithm of the partition function with respect to these parameters, these EAs. And then there's a correction for 0,2. Okay, so these are our, well, our objects which we want to work. As before, we complexify them. Omega 01 is this particular y as before, and then one has to work a lot, and the result after a lot of work is that we arrive at the linear and quadratic loop equations. So here this is the linear one, the quadratic one, we get very explicit formally, so this in homogeneous 0. The notation is a very condensed one. So it's a formal object. These D's, which appear everywhere, they well, add another argument into the W's. X is not touched, and W01 was the Y. So means also these D's, they also act here on this Y and make a W02 and so on. Expanding everything is a horrible expression, but it can be written in condensed manner in this way. And we also have it in genus 1, where it's, so here, this is the linear equation, and the quadratic one is a horrible equation, but essentially we have it. And then, as before, if I want to say here, we get then explicit formally for our WGNs. They are horrible. I will not show you. the projection property does not hold, and therefore we are in the setting of block topology recursion. But we are in better situation. So the original formulation, everything required that these objects here, they should be holomorphic in the vicinity of the branch points. That's enough. And then everything is known up to freedom, which is called blobs. But here we know much more. We have explicit formulae. And then from them, as before, we get really explicit formulae for all omega, so or WGNs, at least for genus 1 and 2. The validity of the local form is completely clear. Therefore, that we are in the blob situation to any genus is clear. But explicit formulae, unfortunately, we only have to genus 0 and 1, because only there, here, the sum of genus is 1. We only have the right-hand side explicitly. So then, final remark, what about other models? Then we do more than lambda phi cube phi quad. For instance, as I discussed with Richard before, very interesting would be Sine-Gordon model. And there is a hint that this might be possible to do. Named together with Gaëtan Bourreau, we found that for any potential which you can have, then if we then add here artificial the BKP time variables and view it as a function, but this should be understood in formal sense, as formal power series, then we get function z of t in form parameters, and this is precisely a power function of the BKP in hierarchy for whatever potential we take. It makes no difference of phi cube, phi 4, or whatever. And therefore, there is a big hope now that the results which I had extend to much more general stations. And primary, formula. So equivalent is to this being BKP tau function is an infinite hierarchy of monotic relations between moments. The simplest one is shown here. So, and this is also something, well, this identity just holds. So for even potentials, so phi to 4, but it would be highly interesting now to relate it to the explicit formulae we had before and to see, in example, how this identity appears from the previous formulae. Is it just combinatorial or do we need more? And that's my plan for the next months or years. Okay, thanks a lot, and I stop here.
Thank you. Let us thank RAIMAR now. Any questions oder Fragen? Andrzej? Adam?
No question. Thank you for the talk.
I have one question, which
go
is
ahead,
very
Adam.
general.
Yeah,
Can
okay.
you show yourself, please?
Show myself is difficult. Well, I mean, I can be
Oh.
seen, yes.
Yeah, I'm
So, thanks for nice talk, RAIMAR. My question is, well, how limited all this is? So this is limited to those sort of matrix models, right? And
So-
matrix approach to non-commutativity, and basically to those phi to some power. So there's no chance of anything
Okay,
like
so
gauge theories or.
okay. So the limitation is here. I'm relying very much. Okay, first, I think this is not much limiting relations. So I need some good noncommutative algebra, and it must somehow be smooth. So Frichet is very natural, and then nuclear is not far away. And okay, then I should identify matrix spaces in it. How general this is, it's not the most general case, but it's not so unreasonable. So what really is limited is this choice, that a scalar product for my matrix spaces, I take this particular one, and this comes from Kontsevich class. So this is really the limitation, well, this 1 over n is okay. It can be done anyway. This is not the point, but that I have a dependence of such a particular form and not something more general. This is certainly a limitation. So the potential I discussed in the end, that for integrability, this does not depend at all on potential. This can be anything.
Okay.
Also, so Sam Gordon would be a very fascinating question, and I'm optimistic that this can be done. But again, with this particular covariance, and I had this in connection with, this particular, so Laplace mass and this harmonic oscillator term with critical frequency 1. This is, there are not much choice, but here the potential can be more or less anything.
Okay, so potential can be anything. Okay, good.
But
Thank you.
It's not, yeah.
Since you have this slide, when you say Moyal space, do you mean something else than the plane?
No, it's the same way, a higher version of the plane. But again, this can be generalized. As said before, this was only for historical reasons. Grossensteiner did it for Moyal.
Because I just looked it up on the internet, and you can have it on the Moyal product on manifolds. So I was
okay, this you mean? Yes, well, if you can formulate it as I said here in this setting, if this is your manifold and Moyal product, then everything is fine.
okay.
The real restriction is this particular choice of the inner product.
Yeah, thank you. Anybody else, Tomek? Hello, Tomek.
I'm good.
You are good.
Okay, thanks.
No other volunteers? All right, if not you guys, no.
So, but I'll unshare, maybe. Yeah.
Yes.
So now I see you.
Okay, so let's thank the RAIMAR again. Thank you.
Thanks for the invitation. Thanks for coming. And yeah, hope I see you in reality at some point.
I hope you appreciate our thanking you in a German way. So.
Yes, no problem. Thanks a lot.
Matthias and I. Okay, great. Let me stop recording, but please don't go away.